Okay, so on to our next thing of notes. So here we're looking at proving segment relationships, and that's about it. So anyway, we have our warm-up here. We need to use the distance formula for the number 1. You need to find the distance between P and Q. So distance formula, if we remember, is the square root of x1 minus x2 squared plus y1 minus y2 squared. So we can label those in our problem here. We got x1, y1, x2, and y2. So we plug everything in. It's going to be -2 minus +4 plus 5 plus 3, because we are subtracting a negative, so we add. So this turns into -6 squared plus 8 squared. -6 squared is 36 plus 64, which is 8 squared. And that is the square root of 100, which is just 10. On the next one, we are given the coordinates of our midpoint and one of our endpoints. We want to find where the other endpoint is. So we need to do x and y individually. So we know the midpoint formula has x1 plus x2 over 2 and y1 plus y2 over 2. There's the midpoint. So we're going to take these out. We don't know what x1 is because that's r. So we're going to look for xr plus the x for s, which is 0, over 2. And this needs to equal the x for our midpoint, which is -4. And the same thing for y. yr plus our y for s, which is -10. We're going to divide that by 2, and that's equal to 5. So we simplify this. We multiply by 2 on both sides for both equations. Cancels the 2 on the bottom of the fraction. So then we have xr plus 0 is equal to -4 times 2 is -8. And yr minus 10 plus negative is equal to 10. So we're going to subtract 0. You don't really have to do that because obviously that's going to cancel regardless, 0. So xr is -8. And we're going to, for the y, we're going to add 10 to both sides. Cancels on the left, and we're left with yr equal to 20. So our r is at -8, 20. Alright, so our notes for the day start with the ruler postulate. The ruler postulate says the points on any line or line segment can be put into one-to-one correspondence with real numbers. So here we have A and B. We know that A is at 0 and B is at 3 because, well, it's a 3-inch line or 3-centimeter line or whatever that unit is. So given any 2 points A and B on the line, if A corresponds to 0, the B corresponds to some positive real number. Segment addition postulate says if A, B, and C are collinear, then point B is between A and C if and only if AB plus BC is equal to AC. So we're going to use these here. We know some other theorems too that we'll use along the line here. So we're going to do a very informal proof for this. Sorry about that. We're going to do a very informal proof for this. And so our first thing is that we know because we're given AB is congruent to CD, or segment AB is congruent to segment CD. That means that AB is equal in length to CD. So this is just using the definition of congruent segments. I'm going to abbreviate some things here. And then we also know based on this segment that we're given here that segment or AB plus BC equals, well, AC. That's our segment addition postulate. Segment addition postulate. We also know, substituting here, we know since AB is equal to CD, we can replace AB with CD. So that means that CD plus BC is equal to AC. This is just substitution. And then, again, off of segment addition, we know that CD plus BC is equal to BD. So this is, again, segment addition postulate. Now we know that using the transitive property, which if you don't know the transitive property means that we can take the middleman out, right? So here we have CD plus BC equal to AC and CD plus BC equal to BD, which means that AC is equal to BD. And this is using the transitive property. And then, of course, going the other way from what we did initially, we know that means that segment AC is congruent to segment BD. And this is using the definition of congruent segments. And that's what we were looking for. So we got our proof of what we needed. Okay, so here's another one. Actually, sorry, here's some properties. So transitive property here, if we didn't already know, transitive property of congruence is the bottom one. Symmetric property just means you can flip the things around. And the reflexive property just means they're equal to the same thing, right? So AB is congruent to AB. So here we have Jamie designing a badge for her club. The length of the top edge of the badge is equal to the length of the left edge of the badge. The top edge of the badge is congruent to the right edge of the badge. And the right edge of the badge is congruent to the bottom edge of the badge. We need to prove that the bottom edge of the badge is congruent to the left edge of the badge. So, here again, we're going to use our definition of congruent segments. Because we're given that WY is equal, not congruent, to YZ. So WY, we can say this is true. Segment WY is congruent to segment YZ. And that's the definition of congruent segments. And then using that, we now know the transitive property is true as well because we have two now. The given has this YZ congruent to XZ. And we have YZ in this one as well. So that means that segment WY is congruent to segment XZ. Time for bee lunch. So this is based off of the transitive property. And then from there we can substitute in, we know, again, based on the bottom one. Block it off there. XZ is congruent to WX, so we substitute in WX for XZ, and we have what we're looking for. WY is congruent to WX. And this is our substitution. So we got what we're looking for. These two things are the same. Alright, so here's a couple more postulates. The protractor postulate says, given any angle, the measure can be put into one-to-one correspondence with real numbers between 0 and 180. And D is in the interior of ABC, if and only if angle ABD plus the measure of angle DBC is equal to the measure of angle ABC. And you can see the picture there. Everything's marked in the colors that go along with it. So here's an example. We have a beam coming out of the ceiling, and so what I'm assuming is happening is here's our wall, here's the ceiling. The beam does this. It's helping hold up the wall, or the ceiling. And it makes a 42-degree angle with the ceiling. So we need to know what the measure of the angle the beam makes with the wall is. So this measure over here. So what that means is we have two angles that are inside of here. And really, I think the picture they really want it to be is something like this, where this is 42 and this is the angle you're looking for. But I don't know why a beam would be coming out of a wall like that. So that said, hopefully our wall makes a 90-degree angle with the ceiling. And since it should do that, we can just take our 90 and subtract 42 from it, and we'll get the length, or the measure of our other angle. And that would be 48 degrees. Super simple. So that is based off of these theorems here. A supplement theorem says if two angles from a linear pair, or two angles form a linear pair, then they are supplementary angles. And the complement theorem says if the non-common sides of two adjacent angles form a right angle, then the angles are complementary angles. So here, once again, we have a clock. We know when that's 4 o'clock, our hour hands at 4, minute hands at 12, and the angle there is 120 degrees. So this is 120. And it says when the second hand bisects the angle between the hour and the minute hands, what are the measures of the angles between the minute and second hands? So bisect means that it cuts it in half. So that means that our two angles here, this one in red and this one in blue, are the same. So we just need to take our 120 and divide by 2. It's 60 degrees. So here's some more properties of congruence. These are to angles and the congruent supplements theorem, the congruent complements theorem. So if two angles are supplementary and then two other angles are supplementary, then the first and the last one are congruent. And then the same thing for complementary, but just to 90 instead of 180. So here we have angle 4 and angle 1 are a linear pair. measure of angle 3 and measure of angle 1 are 180. We need to prove that they're congruent. So we're not going to do a proof like we had been doing. I'm just going to show you. So we know that that angle 1 and angle 4 are a linear pair. This tells us that the measure of angle 1 plus the measure of angle 4 is equal to 180. We also know, given to us, the measure of angle 3 plus the measure of angle 1 is 180. So we can set these two equations equal to each other. We can have the measure of angle 1 plus the measure of angle 4 equals the measure of angle 3 plus the measure of angle 1. If you notice, we have a measure of angle 1 on both sides. So if we subtract it from one, we subtract from the other. At the same time, they're going to go away. So now we are left with the measure of angle 4 equal to the measure of angle 3 which we can rotate around, but either way, that means that angle 4 is congruent to angle 3. Didn't know those were coming up. But basically just what we just did. So okay, so now same process kind of as we had before. We have two angles that form a linear pair, two other angles that form a linear pair, and two angles that are congruent. We need to prove these other two angles are congruent. So we know that angle NYR, the measure of it, plus the measure of angle RYA is equal to 180, because it says they're a linear pair. And the same thing for the measure of angle AXY plus the measure of angle AXZ. That equals to 180. And we also know that the measure of angle RYA is equal to the measure of angle AXZ. So I can substitute that in and set these equal to each other like we did before. So we have the measure of angle NYR plus the measure of angle RYA equal to the measure of angle AXY plus the measure of angle AXZ. And we just said that RYA and AXZ are congruent, so that means we can replace one of them. The measure of angle NYR plus the measure of angle RYA equal to the measure of angle AXY plus the measure of angle RYA again. And again, we have RYA on both sides, so we can cancel those. Then we're left with the measure of angle NYR equal to the measure of angle AXY, which means that angle NYR is congruent to angle AXY. Which is exactly what it asks us to find. Vertical angles theorem says that if two angles are vertical angles, then they are congruent. If the angle 1 and angle 2 are vertical angles, and the measure of angle 1 is equal to d minus 32, the measure of angle 2 is 175 minus 2d, we need to find our two angles. So, because they are vertical angles, we know they're congruent. That's what we literally just read on the last slide. So we can take this and do d minus 32 equal to 175 minus 2d. Add 2d to both sides. So 3d minus 32 is equal to 175. We add 32 to both sides. And 3d is equal to 207. And we divide by 3. Guys are rude about opening the door. And comes out to be equal to 69. So now we're not done. We found what D is. We need to plug D back into one of these two equations. Since we know they're equal, we'll get both of them out in the process. So the measure of angle 1 is equal to 69 minus 32. So when we subtract that, the measure of angle 1 comes out to be 37 degrees. And since we know they're congruent, the measure of angle 2 is also 37 degrees. And that's it. So now we have some more theorems. Perpendicular lines intersect to form 4 right angles. All right angles are congruent. Perpendicular lines form congruent adjacent angles. If 2 angles are congruent and supplementary, then each angle is a right angle. And if 2 congruent angles form a linear pair, then they are right angles. And here's your exit ticket.